So during the talk, you will realize what's meant with intertwined entanglement in topological pumps. Let me start slightly somewhere different. So some of you might have thought about at some point, about building a quantum computer, and and then you have to make choices, and one of the big choices would be whether you use synthetic qubits, so like superconducting qubits or spin qubits, some solid state type of device, or natural qubits, atoms, ions, and photons. And then those different approaches have their distinct challenges. For example, for the synthetic qubits, it's difficult to make them identical. And also, if you think of superconducting qubits, to connect them is not necessarily easiest thing if you want to connect all to all. But of course, also for atoms, for example, and ions, it's not all easy because there the challenge is, of course, to position your qubit. So the difficulty is not in building it, but in positioning it, in transporting it, and also to connect them. And there is a scaling challenge, which kind of all approaches share. And in my talk, I will address the transporting and the connectivity challenge and the scaling challenge. But let's first step a bit back and zoom out into the different developments in history of humans. And I think one big challenge was to transport cargo like copper ore. And there was the development of the wheel. It was stepwise. For example, there were first the rollers, and then finally the wheels. And nowadays we are very sophisticated in all sorts of wheels. We are now in a time where the challenge is the transport of quantum cargo. So we have to learn how to transport qubits, entangled states. And also, I mean, what I like in this comparison, this was not done within a year on the left-hand side. It took some time. So we are in front of a journey. And in this talk, I will show you how we use topological pumps to first take two singlet pairs, and we use them to split the pairs and then let them pass through each other. That's where the intertwine comes from. And then move them back and check whether we have lost information or not. And then the scaling challenge. I mean, if you think about entanglement, then sometimes you wonder, where is the entanglement in nature? But then, okay, it's everywhere. I mean, all our filled orbitals in any molecule, they are entangled pairs of electrons. So massive entanglement. And one then wonders, couldn't one use that entanglement? So you have a pair, electrons spin up and spin down. And then often it's said, oh, this is useless entanglement. But if you are able to move those pairs out of the orbitals into two different orbitals, then you can make useful entanglement out of it. In particular, or that is crucial, the process needs to be reversible. Otherwise, you've actually lost. And then also what you would like is to move them out of their orbitals and then maybe let them interact with another pair and then bring them back and maybe measure. So, but with electrons, this is a bit too fiddly to get them out of the orbitals and in again. However, with atoms, this is okay, much more promising. Because in atoms you can use singlet pairs, like in fermions you can have paired, massive amounts of paired fermions. And to accomplish that, we let matter and light work together. And our starting point is a cold Fermi cloud of potassium 40. And with attractive interactions, you have in the cloud maybe 80% of Feshbach pairs. And then we switch on an optical lattice. And so they localize, and these pairs, then you have roughly 80% of the atoms in pairs on different sides. Not completely full, there are holes in between, maybe 60% of the sides are filled. And of course, the physics of this system can be described by the Fermi-Hubbard model. So basically, you have the atoms hopping from side to side. And what we now mostly have here in our system, that you have two on the same side, and you can control, and that's important, you can control the interactions. An important point to how we will actually measure on the system. And that we do with Stern-Gerlach spectroscopy of the pair. So imagine you have atoms, you have sites with a single atoms and with doubly occupied sites. And now, due to control of interaction, we can turn the doubly occupied sites, the green atom, into blue atoms by doing precise spectroscopy, and then Stern-Gerlach expansion, and then measure. Okay, so these are the ingredients, and now, most importantly, let's talk about lattice geometries. Because the interaction, we understand, we can tune that with Feshbach resonance. And the lattice geometries, usually what you think of is, we have two standing waves, and if we have slightly different frequencies, then interference terms we can neglect, and you get such square lattices. But you could also consider having the same frequencies here. And now you realize, okay, if I have two standing waves, there is one relative phase, and that's the time phase between those two. Are they swinging in lockstep or just opposite? If they are swinging in lockstep, then you get such a checkerboard pattern. And now you can overlap these patterns. And then you get lots of different possible geometries, and also you can shake, for example, the whole system, and then you get topological effects. However, what we want to do here is something that we have overlooked, our community has overlooked. What one can actually make rather easily is to move one pattern, here the yellow one, with respect to the red one. And that will allow you to create extremely robust topological pumps. I will come back to that. So that's a view of the experiment. And since it's you, I will give you an inside view of the experiment. And you probably will not be surprised. On the one side, many lasers, on the other side, vacuum in the background, or the computer control. But most importantly, here is a team running the experiment. And Konrad Fieban, he's a senior postdoc on this experiment. And Jan Kief, another postdoc, and Sichia had done his PhD and is at the moment also working as a postdoc. So remember, we had this 3D lattice, and we have singlet pairs on those lattices, attractively bound like Feshbach molecules. And now I think I could also convince you that we are wizards of constructing different geometries of optical lattices. So we can imagine that we can also create lattices of double wells and control them. And now let's look at a singlet pair in a single double well. And now we have we can tune the interactions from attractive to repulsive, and we can control the double well. And what this allows us to adiabatically transfer this singlet pair, which is localized on one side, we can convert it into a Heisenberg singlet, which is basically a correlated Bell state, where either I have different spins on the two sides, but I don't know which on which side. And now these are still quite close to each other. So what you really want is now to move those singlets apart. And for that, we use a topological pump. So let me remind you of the topological pump. So the implementation is you have a static potential with periodicity, say lambda, and then you have a moving potential with a larger periodicity, twice the periodicity. So you get a time and space periodic potential. And it is characterized, this potential, by a sublattice offset, which is labeled here delta. And then you have two tunnelings between the dimers and tunneling on the dimers. And so you have two tunnelings and you have a difference between those tunnelings. And now you can, then the difference between the tunnelings is relevant. And now you can perform, when you move this lattice, what you perform is a circle in this space on the right-hand side. So you vary the delta T, so the relative tunneling, and the sublattice offset. And as long as you don't hit the zero, where you have crossings, then you do perform a topological pumping, which means that you can either transport an insulating state or localized Wannier states are also transported exactly per cycle. They are moved by one unit cell. So one can look at it in a picture. For example, there on the upper left, that is a state localized on this double well, and then you do this movement. You move one lattice with respect to the other, and you will see that this state transforms in a Wannier state on the next side. And then if you move another quarter period, then you have moved the whole state by one lattice side, and so forth. And now you could, of course, argue, yeah, okay, I have this long period lattice, and if I put an atom in there, move my lattice, it will also have moved there. Yet there is one thing that is non-trivial about this transport, and that is when you now look at the next highest state. So what you have in this topological pump, you have you have your lattice, and then you add this long wave lattice that leads to a band splitting. Okay, and what you end up is with a band structure where you have a lower mini band and an upper mini band. The lower mini band, that was the movement that I had just shown you, and the upper mini band, there the particles are moving exactly in the opposite direction. So this means, and well, these reflect the different Chern numbers, 1 and -1. And besides this movement in different directions, what is also, and it's I mean it's a topological and adiabatic process, so there's no energy exchange with your fields. So it's very nice for coherence. And also, what is nice is the big energy gap to the next higher bands. That is an advantage compared to the shaking of the lattices. When you do Floquet engineering, the usual Floquet engineering, where you mix in higher bands, you might end up with some atom fraction in the higher band. If they then collide, you don't get them back down. This is not the case here, and this allows you to look at topology in the presence of interactions. Okay, so how do we implement them? I've told you already a little bit. We can create these square lattices, and then we can create a second lattice on top of it, and we can move it. Okay, and then if we have strong enough beam in one direction, then we will have 1D tubes with these topological pumps. And an important point here is this method is very robust and can be implemented by beams where one beam is just slightly moving in frequency with respect to the other beams. And the standing wave, and that's what had been overlooked. Usually, your standing wave, you write down, this wave comes from this direction, same is reflected back. But here, if you reduce the reflection back somewhat by some percent, then you actually get the moving pattern as is illustrated here. And it avoids, if you had 1064 nanometer and 532 nanometer, then you have a problem in making these topological pumps. And that is that the refractive index of air behaves very differently at those two frequencies, and any changes due to change in humidity, temperature, and so on affects your lattice. So here it's almost the same frequency at 1064 nanometer, and you can create these systems. And I mean, as you know from experiments, sometimes you think something up and then you try to implement and it takes ages. Here it was different. Actually, it worked um, immediately. So here you see these were one of the first pictures where the whole cloud is moving to the right, and you see a little bit of population moving to the left, which is also partly populating the higher miniband. I should also say that the way we realized this was that we did an experiment with a cavity and had a self-organization and suddenly saw a movement of the cloud in a perpendicular direction, and that was COVID time. So we had to think and had time to think and understand, and that's how we realized the role of the not perfect back reflection. Okay, so let's look at the topological pump with interactions, and you can now move these cycles and then monitor the center of mass, and you see that it nicely falls on a line. And with interactions, you also see that it's robust with respect to interactions. Up to a certain point, if you have too strong interaction, when interaction is on the order of 2 times the sublattice offset, then the topological pumping breaks down. But that makes sense. And now, since the process works extremely well, you in the experiment, you just let it run and it pumps, and you have a harmonic trap, and then you can wonder what's going to happen. And funny enough, there was not so much literature on that. There was one paper with a gradient where they did predict a reflection, but you could also read that it gets stuck or something like that. So we did that, and what we see is actually that it is reflected. So you pump. So these are different slices, always a bit later. Uh, Here you see the dashed line that it is reflected, and here some linger on, but then they disappear and are also reflected. And you can also associate this with a churn marker here. When the trap is not too steep, then you have a churn marker 1, and then it should give nice topological pumping. And here the turnaround happens when also churn marker goes down. And you can imagine 5 minutes. Who speed up? Okay. The key point is the gradient will of the trap will compensate your sublattice offset. And what you get is a region where you have topological trivial and topological non-trivial part. And now you can do the same with interactions. And what you see then is actually a second region where it is reflected earlier. And that happens when the interaction and the topological and the sublattice offsets added give you the level of energy as a gradient. So you have kind of an interaction-induced change of barrier of where you are topological or not. And you can also see that if there a pair comes, it split the pair. That's where we were then thinking about splitting the pairs. Okay, now let's come back to the topological pump and the pairs. The first question one might ask are, how well can we pump the pairs? And there we get fidelities per cycle of 99.5%. So it works extremely well that they stay pairs. Now let's do the splitting and recombining. Okay, so we split with controlling offset and interaction. And then to measure whether we have a singlet, whether we do singlet triplet oscillations, by applying a magnetic field gradient, we mix singlet and triplet states, they oscillate, you then move back and then measure again whether you have the singlet state. Now you can do the step in the middle, that is, you switch on your topological pump, and now again do your singlet triplet oscillations. And now, since they are much further away, you expect a much higher frequency in these singlet triplet oscillations. And that is exactly what we see. But now you might ask, well, here it comes back, and here we bring them together. Okay, but now you might ask, but what is happening? I have two of those pair not too far away, and they want to pass through each other, but may not be able. And that's where we implement swap gates so that they can pass through each other. So this is where the intertwined entanglement comes, okay? So they come, and now we do, for example, a super exchange interaction, and then we have a swap gate, and they can move further. That's why we can get actually these large distances, because they all pass through each other. We can, and then you see correspondingly higher frequencies in that set of measurements. We made up to 19 sites apart. And that's also what this animation reflects. But since I'm running out of time, you can also apply variable swap gates. That depends then simply on the speed or the interaction strength of your lattice or your topological pump. And you can do swap square, then they are reflected. You get additional frequencies in your spectrum. that's shown here. And with this, I'm coming to an end. And you can have in these systems full control over external and internal degree of freedom. You can extend it in a higher dimension. You can move in other direction. You can, in particular, you can move them through each other and then change the interaction and then entangle far away particles. You should also be able to do mid-circuit measurements. It's scalable, and one can also do quantum enhanced interferometry. So we are very upbeat on that, and sometimes I'm wondering. Usually, I'm a big fan of quantum simulation, but it came to my mind that maybe it is easier to build a quantum computer than a quantum simulation of a ground state. And the reason being, well, the quantum computer on the one hand has not many applications, that's sad. Quantum simulation has many open questions to address, so, well, it's sad. But the reason is that in here, if you can move your particles and let them interact at deliberate points, you can create rather complex entangled state, but they are not at equilibrium. In quantum simulation, if you want to simulate a ground state, it needs to equilibrate, and that is a challenge and time consuming. So that's why I'm at the moment very upbeat on quantum computing, and I would like to thank also the other teams in my group. It's a great pleasure to work with each of them. And thanks for listening, and thanks for the 1.4 minutes extra.
Yes, fantastic. Let's applause. Yes, and we can take a few questions. Maybe start with you.
Hello. No, thank you for the brilliant talk. It's very interesting. I just wanted to ask, in terms of the actual topology of the pumping. So you said here that you're kind of working with like one has Chern number, these mini bands with Chern number +1 and one with Chern number -1. But there are like other pumping models that can give you quite a lot of Chern numbers, like an AAH model, for example.
Okay.
So can you have the situation where you might have one coming from a band that has like a Chern number of +2, another one with a Chern number of like -1, and so one's traveling a difference, or?
I could imagine that that's possible. We have not deeply looked into it. Here, the very nice thing is that it's so robust, but one can play more with the geometry. So this is just rudimentary in that sense. And of course, for one can also imagine that you add tweezers on that, and then you locally change in which direction it goes. And that would be, that would be digital, because either tweezer on or off, no fine tuning necessary.
Thank you very much.
Thank you. Yes, there is a question now.
So thank you very much for the very nice talk. So I had a question related to this outlook of using this platform for computation. So in the thesis you have mentioned, as far as I understand, the control of the lattices is kind of global. So you have an additional lattice, with a double the frequency that you control to make the pump. For this idea of doing computation, you would need some kind of single site addressing of your atoms. So how do you envision that?
Oh yes, yeah. You need a bit of the toolbox, but in principle, I think it's easier to create initially a product state in the lattice than these states that you want to thermalize. And then out of the product state, by deliberate interactions between this and that particle and so on, that you don't need to thermalize, so it should be faster and more feasible.
Okay.
And I should also say we get these swap gates. Our latest, not yet published version has a 99.89 fidelity, averaged over 20,000 qubits. So it's quite remarkable.
Sounds impressive. So thank you very much.
Okay, thank you. I think we could move on, and let's thank the speaker again.